Hi everybody, Dr. Joel here. I'm not in the Quayside office. I have a layover day here in Berlin, Germany, and so I thought I would take a few minutes to talk about another video. So I've got some requests to do a video on the way mixers operate, and I learned from an old hand at HP about his perception of the way mixers operate, and I think it's the right way to think about it. So I've got some slides from a couple of years ago. I'll go through those, and maybe we'll all have the same understanding about how we can view mixers, and that will help us understand how we can measure mixers. So let's get started. So today's topic is, what are mixers? How do they work? Why do we care? And I'll go over some mixer design. On the left you see actually my first design at Hewlett-Packard starting about 1983. I designed the first down converting mixer in the 8753 source. It had a LO that ranged from 3.8 to 6.8, had a fixed frequency input of 3.8 gigahertz, and you can see what came out was 0 to 3 gigahertz, 0.3 megahertz to 3000 megahertz, and learned a lot about mixer design and mixer testing. So today's topic is going to be mixer design and how mixers operate, and then in a later video I'll talk about more details of mixer and frequency converter test. So when we look at a mixer, one of the common ways that at least I learned in college that a mixer worked is you had some nonlinearity, usually a diode or a transistor operating in a nonlinear region, and you put in two input signals, a LO voltage signal and an RF voltage signal, and then they would say, well, the input voltage is equal to this kind of Taylor expansion of the curve of the nonlinear, and they would point out there's a second order term, and if we take that second order term and we go a bit farther with it, then they tell us, oh, it becomes a sine. You take two cosines, you square them, and then someplace out of all that math drops the difference between two frequencies. And this is not the way mixers work in practice. I have never seen a mixer that operated this way. An ideal mixer, it doesn't actually mix, it multiplies. It multiplies essentially a chopping signal from an LO. So here is a representation of that single balanced mixer. We have a local oscillator coming into the mixer, and it's essentially multiplying the RF by essentially an on-off wave. So it's basically chopping the RF at the LO frequency. And so the idea is, in general, you drive these diodes as hard as you can, maybe even with a square wave, to get them to turn on and off really fast. And then what you end up coming out of this is a chopped version of the signal. And if you kind of draw a notional underlying signal in here, you'll see that you end up with having a lower frequency, and that lower frequency is the difference between the LO chop cycle frequency and the RF frequency. Single balanced mixers were useful, and we used them a lot in the early days, but now more modern techniques move us almost always to double balanced mixers, and then sometimes even triple balanced mixers. The double balanced mixer has two nice advantages. It suppresses even order products, and it also has the attribute of having a higher conversion, less conversion loss, higher conversion power, because you get a combination of the single balanced chop cycle plus you invert the single balanced mixer and add it in, so you get more power. So this is kind of a representation of what will come out if I chop the RF signal over the positive side. Then during the negative conduction, the RF signal is essentially inverted, and then during the positive next half cycle, the RF signal is chopped again. And sometimes they call this a commutating mixer. If you don't know what a commutator is, you can do what I did. Go to Oregon State University and take your electrical rotating machines class, and then you'll know what a commutator is. This is an example of an ADS circuit layout for a Gilbert cell mixer, and it does almost the same thing. So I'm kind of drawing here in the black. The LO signal is coming in, and it's turning on and off these current sources that are driving this differential amplifier. The RF signal comes in differentially, and on the positive half cycle of the LO, the RF signal goes here. And on the negative half cycle, the RF signal goes this direction in this long red arrow. And the other portion of the differential pair during the negative half cycle that's not wanted gets dumped to the load element. So then this output amplifier amplifies the IF signal, just But we're not multiplying here, we're really chopping the signal or commutating the signal. So let's talk about frequency conversion and what I like to call the normal and image mode of a mixer. So here I'm showing the local oscillator is right here in the dark gray arrow, and the input signal here is in this light gray, and I'm showing this little arrow here to indicate maybe the signal phase or direction. So let's suppose it's a little radar chirping in positive in frequency. Well, when you mix that with the local oscillator, you're going to get a low frequency signal, the difference of the products, and a high frequency signal, the sum of the products. And in both cases, those signals are going to move in the same direction. Now, there's another mode of mixer operating, we'll call it image mode, and here I have it's an up converter where the input signal's sweeping up in frequency here. We have the local oscillator here, and we can actually up convert to the positive side or the high side of the LO, which in case the signal moves in the same direction, or the low side of the LO, in which case the signal moves in the opposite direction. That is, the frequency moves down at the output when the frequency moves up at the input. And that has a particular meaning mathematically. Let's talk about that. So here's a representation of an ideal mixer. This was from a paper I did with a group from NIST. And in that paper, we talked about the proper representation of the linear operation of a mixer. And maybe I'll pause here to note that the mixer, if we go back a couple, 3 slides, when we look at this mixer, or the double balance mixer, you might think, well, it's really nonlinear because it's being chopped. But in fact, in the transfer of RF to IF, it is almost perfectly linear because these diodes act like switches. So when they turn on, they don't cause any distortion of the portion of the signal that's sent from the RF to the IF. So if the RF signal goes up twice in power, the IF signal goes up exactly twice in power. And if you had a modulated signal at the input, you would get a modulated signal at the output. You wouldn't see necessarily distortion as long as you're not driving this RF signal too hard across these diodes, as long as the RF signal input is small relative to the diode size. So one of the ways they make mixers more linear is they stack more diodes in this diode stack. They drive it with an even bigger LO, and that gives you more power that you can put into the mixer before it starts to change the conduction angle of the diodes. So where that leads us is for a standard mixer, if we try to say how much RF output signal is due to the IF input signal or the RF input signal. Now in this case, what we say is this mixer is ideal. So we put a 0 here and here. These would be kind of the reflection terms. So if ARF goes in and it has a 0 here, none of this BRF signal comes out according to the ARF. But if AIF, the IF input signal, the A waves, meaning the instant wave, goes in, then the amount of signal that comes out is multiplied by the ALO. And this LO signal, we always treat it as though it is a kind of a constant magnitude 1. That's because the idea is when you drive the diodes hard enough, if the LO power changes, their conduction angle doesn't really change. The phase will change. So this is a way of representing phase of the LO. Now, if you have an image mixer where the LO, that's where the LO signal or the output signal is going to be below the LO, then you end up with an interesting characteristic that the image signal, the signal coming out here, is actually multiplied by the conjugate of the local oscillator. So it's the input signal AIF times ALO conjugate. And that conjugate is what gives us that reversing phase or reversing frequency behavior. And normally, you might not think too much about it, but if you were to look at, say, the modulation waveform, it would be chirping down in frequency instead of chirping up in frequency, and that's how we represent it. It has a big consequence when we go to modeling mixers where they're no longer ideal. So if you have a mixer that has an input signal or an input reflection and an output reflection, we can actually combine those together if we do it in the right way. And the right way to combine those signals together is to remember that if you're moving in a normal mixer, you can move the IF block over to the RF block, so we can move this block over. We don't really need to do much with the frequencies, but if it's an image mixer, when we move those over, we actually have to conjugate the terms of the RF side to move it to the IF side, or the IF side to move it to the RF side, to represent the fact that the spectral content or the modulation waveform is going to be inverted, and so the effects of reflections and re-reflections need to be conjugated as you move a match term from one side of the mixture to the other. Now we have to accommodate this in our error correction. So if you look at the error correction terms in V&A, when we do a full mixer match corrected error terms, the error terms have to be internally conjugated to get the right error correction. So you can also model your mixer as either being IF referred or RF referred, and we can treat this mixer kind of like a single block. Sometimes you want to do things like in a millimeter wave system. You might want to have an up converter and a down converter, and you'd like to de-embed that from the normal measurement scenario. And you can do that by just creating a single block that has the representation of the mixer as an IF or the mixer as an RF. But you have to be careful if you're going to do that and move it to create essentially a single block at the output. So if I wanted to model this as a single block, I'd have to be sure to conjugate the output terms or the input terms as they're referred to the output. And same thing with the source match. If I were to look through here and look and see what is the apparent source match effect on an output reflection of this lower mixer, I would have to get a conjugate of the source match to get the proper behavior. So that's a tricky thing about image mixers and something we have to be aware of. And then we'll take a little bit look at more complex mixers. So here we have an example of a hybrid mixer. For a hybrid mixer like this, we can represent it as a single sideband mixer, or you can also represent it as a image reject mixer. And so for this representation, let's talk about the input RF signal. And imagine there are two tones on the input RF signal, where the LO is where this red line is. One of the signals is above the LO by the IF frequency, one of the signals is below the IF. And let's, for this experiment, pretend that both of these have zero phase. We'll represent zero phases facing straight up. Well, when they come through the 90-degree hybrid, they still have zero phase. When these two signals come through the cross link, the 90-degree link, then they'll have 90 degrees of phase shift. When they go through the mixer, this mixer is going to conjugate the low side signal. So the conjugate is 0, and both signals, the arrow signal and the dot signal, have 90 degrees or 0 degrees phase shift. But on this lower mixer, this low side signal is conjugated, so it becomes minus 90 instead of plus 90, and the little dot signal becomes 0. So now let's look at the two outputs. We have an IF output and an image output. The IF output is going to have this main signal pass through the zero path, and this 90-degree shifted signal pass through the 90-degree path. So the main signal comes out, there's no change. This signal passes through the 90-degree path, it's shifted 90 degrees, and so now this becomes 180 degrees, 90 plus 90. And the arrow signal, because it was minus 90, gets shifted up to 0. And then the two sum together, and we only get the arrows. So this is an image reject mixer where the rejection is the high side signal and the low side signal is passed through at twice the strength. On the other hand, if we take the output image signal and we look at that, well, both of these zero signals pass through the 90-degree path, so they're shifted 90 degrees. Both of these pass through the zero path, so they shift 0 degrees. So the arrow is plus and minus 90 degrees, and it cancels. The dots are both 90 degrees, and it comes out with a 90-degree phase shift, twice the signal. And now this IF signal represents the high side signal, down converted to the IF, and the low side signal is image rejected. And pretty obvious from these plots, if your 90-degree shift isn't really 90 degrees, then you're going to get a little leftover signal from one of those paths, and that signal will show up as a little error signal overlapped on our IF signal. Image reject mixers can also operate as an up converter. So here I have, in the lower plot here, I have an up converter version. They can also operate digitally. So here I have an RF signal that's split. It goes to two mixers. In this case, I'm putting the 90-degree hybrid on the LO path so that this output signal is shifted 90 degrees with regards to this signal. And then these two outputs, which we often call the I and Q path, where here the LO passes through 0, so this I path has 0 phase shift. The LO passes through 90 degrees on the hybrid, so now this has a a 90-degree shift on the signal coming in. And then we might sample those with ADCs and add them numerically. And when we do that, we also get a numerical image rejection. So even though we get two signals out here and two signals out here, we sample them both with the ADC. The image signals are rejected. And in an up converter, we can drive an I and a Q input signal. You can get that by putting another hybrid at the input, or you can drive it with two different signals. This is classically what's done with a dual channel ARB or dual channel ADC, where you have an I signal and a Q signal. You put them in, we have the 90-degree hybrid here. So this is shifted 0 degrees relative to the LO. This is shifted 90 degrees relative to the LO. Then we sum the two outputs at the RF output stage, and that becomes a up converter signal. And depending on the phase shift, we can either get an up converter with low side up conversion or up converter with high side up conversion, and we'll still have image rejection. And we can do a lot of these measurements on the P&A. I'm not really going to go into the P&A measurements this time, but I am going to take a chance to just show them one measurement. So this is showing the measurement of a signal coming out of a mixer, and I'm putting an RF signal into the mixer. So this is representing the output signal at the output of the mixer, and what we're looking at is all the other stuff that's coming out. So normally we just expect the IF to come out. And in this plot, what I've done is I've shifted the signal from its initial input signal of 10.25. I shifted down to, or started out at 10.3, shifted down to 10.25. So I shifted the signal here, and what I see is the IF signal also shifts down. The yellow signal didn't shift, of course, because I'm not moving it. And I see this little signal here. That signal is the image of the second order term. So we see number 7. It's actually 3 times the yellow minus 1 times the RF. So since it's got that minus sign in it, when I shifted the signal down on the input, the signal went up on this higher order product. Then here I have a 5-3 product, and this one actually shifts 3 times the range. That's this number 9. It shifts 3 times the value for 1 time value shift in my RF input signal. And number 8, that's 2 times the LO. It doesn't move at all. And then the RF plus, the image signal, which is plus signal, actually you can't see it because it's kind of hidden behind this graticule line, but it shifts down 1 when the RF shifts down 1. So it's moving in the same direction as well. So because both of the outputs, the LO plus and the LO minus, shift in the same direction, we would say this is not an image mixer. Then what we're seeing down here is a bunch of higher order terms. I didn't identify all of them, but we can see these are probably second order terms because they look like they shift 2 times for each signal. So probably have a bunch of second order terms in there. And this just goes to show that when you make a mixer, you get lots and lots of things that come out of the mixer, and you have to be really careful to not have those spurious signals, or they're called mixer spurs, but I prefer to call them higher order mixing products, come out of your mixer. So how do we determine where those are and how we might design a mixer chain? And usually we do multiple up and down conversions in order to make sure that the spurious or higher order product signals don't land in the channel that we're interested in. So this represents an up converter, and this white triangle is the IF, and so down here in this lower plot I plotted 3 times the IF, and the dark gray 2 times the IF. And here's the LO signal, and here I plot on the same axis scale 2 LO, 3 LO, 4 LO. So I've kind of done a geometric construction of the spurs. So if we take 2 times the IF and we say I want to make the 3 times the LO minus 2 times the IF, this is 3 times the LO is here, minus 2 times the IF is here. It's this gray triangle right here. And this upper triangle is the desired output, which is RF equals LO plus IF. And as it's sweeping here, this is sweeping down, and at this frequency, we're going to get a crossing spur right there. Same thing with the 2LO minus IF. So here's the 2LO, here's the IF, so we can take this point and subtract it from this point, and it starts here, and we can see that this will be a crossing spur right here. And then we see 4 times the LO minus 3 times the IF, and I do my construction, and sure enough, I'm going to get a crossing spur right here. So where the two amplitudes are the same, that's where I get a crossing spur. So this, I hope, helps you understand how mixers operate and how some of the higher order products are generated and where they might show up in your mixer diagrams. So I hope you enjoyed that explanation of at least how I think mixers and frequency converters work. We looked at some of the operating conditions and how the higher order products are created. And in another video, I'll show you some of the ways that we can measure these mixers, the higher order products, and all the attributes of them. But for now, my flight's in 30 minutes, so I should get ready to go. Thanks for watching.